Far away from the sun, in the deep regions of space, temperatures fall to an incomprehensible cold, minus 450 degrees Fahrenheit. Planets closer to the sun have temperatures in the thousands of degrees. Separating Earth from these extremes is a cocoon of gases called an atmosphere. Weather describes conditions in this atmosphere. Most weather happens in the troposphere, the atmospheric layer closest to Earth. It stretches from the ground to about 10 miles up. Here, gases and water that make up air mix and whirl with energy provided by the sun. Some of these gases, particularly carbon dioxide, help retain heat instead of allowing it to escape into space. This heat keeps the Earth warm enough for life. Water vapor comes up into the atmosphere from oceans. It collects on small particles in the air and forms clouds. When enough water or ice collects in a cloud, it rains. If the temperature falls low enough, rain turns into snow. Each cloud signals a different sort of weather. Tall, dense, cumulonimbus clouds spell trouble, like thunderstorms and tornadoes. Wait long enough and weather changes. But climates take decades, even centuries, to change. The Earth's history is written in climatic change, periods of cold and warm. Seen on a geologic scale, climate is no more stable than weather. Some scientists believe we are living in a short warm spell between ice ages. Others think human activities, such as burning fossil fuels, may be heating the Earth to an all-time high, but no one knows for certain. Climate forecasting is just as difficult as predicting the weather. Water blankets nearly 3/4 of our planet and sustains all life. Warmed by the sun, seawater evaporates as invisible gas and is carried high on the wind. Waves toss salt crystals into the air. Wind and forest fires send more particles into the atmosphere. As water vapor cools and condenses, this particulate mix becomes a cloud. Heavy clouds, like this full-blown cumulus, can weigh 500 tons. At the top of the cloud, water is frozen into ice crystals. As the ice crystals fall, they heat up and melt. Individual water droplets float so lightly, each one would take most of a day to fall all the way to the ground. It takes 1 million of them to form a real drop of rain. Scientists actually have a test for rain. To pass, a drop must measure 2/100ths of an inch or more. Smaller drops fail and count only as so much drizzle, the thin mist that comes from stratus clouds, like these. So how do you catch a raindrop and measure it? Here's the recipe. Fill a tray with 1/2 pound of sifted flour. Put the tray out in the rain for a few seconds. And then bake it in the oven for 20 minutes at 350 degrees. Sift the flour again And you'll find raindrops cooked to perfection and easy to measure or eat. Rain falls when moist air is forced to rise. Cold fronts produce the heaviest rains. Cold air weighs more than warm air. And as frigid fronts move in, they shove warm air higher into the atmosphere, where it cools quickly and condenses into rain clouds. Warm fronts create lighter, steady rain. Warm air approaching cold weather slides over it, and thin stratus clouds form. Where the air is dry, rain may evaporate before it hits the ground. The rim of the Grand Canyon absorbs 16 inches of rain a year. 5,000 feet below, the foot of the canyon receives only 6. Streams of rain that evaporate on the way down are called virga. People in the flood-prone regions of the world may wish for virga. Floods cause more death than any other act of nature. A bath full of water weighs 3/4 of a ton. A river just 2 feet deep can drag a car away. But all life needs water. Regular torrents make rainforests luscious. In Asia, 6 months of monsoon provide prime conditions for growing rice. Rain both gives and takes life in its roundabout cycle from Earth to atmosphere and back. Storms and violent weather take millions of lives each year. Some of the most destructive begin quietly off the coast of Senegal in West Africa. Unremarkable storms warm the ocean and pick up spin from the Earth's rotation. The worst are sent swirling across the Atlantic as hurricanes bent on destruction. At their most powerful, hurricanes spread 1,000 miles across and wheel at 200 miles an hour. A storm that size can inhale 2 billion tons of water and creates enough power to satisfy the energy needs of the U.S. for the next 100 years. Each year, the Caribbean and Florida suffer warnings and near misses. But when hurricanes actually hit, devastation is certain. Richard Horodner courts disaster. He chases storms for a living. Horodner was there when Hurricane Andrew hit Florida in 1992.
The sound was terrific. There were just trees pounding up against the walls. There were cars flipping. There was glass flying all over the rest of the house, shingles being embedded in the walls. It was an hour of just hunker down and hope for it to be over.
Andrew caused $20 billion in damage, and even this paled next to the devastation wrought by Hurricane Mitch's sweep through the Caribbean in 1998.
The biggest danger in a hurricane, and this is where 90% of people are killed, is by the tidal surge. 90% of deaths are caused by drowning in a hurricane.
Tornado Alley in Texas, Oklahoma, and Kansas. These storms twist at 300 miles an hour, moving houses and tossing cars in an instant. Here, as many as 1,000 tornadoes a year begin when warm, wet air from the Gulf of Mexico is pushed high into the atmosphere by a cold front moving down from the Rocky Mountains. As the warm air cools, it condenses as a giant thundercloud. The worst thunderstorms produce so much energy, a funnel bursts out of the bottom of the cloud and speeds to the ground. The most violent and destructive touch down as tornadoes. Though most tornadoes exhaust themselves in minutes, they can destroy everything in their path. We've grown much better at predicting violent weather and moving people out of harm's way. But hurricanes and tornadoes still leave destruction in their wake. Today, people living in big cities like New York make their own weather. Each year, Manhattan produces over 1 billion kilowatts of energy per square mile. This adds about half as much energy as the sun naturally provides. So New York, in effect, lives under 1.5 suns. Climatologist Dr. Stephen Schneider describes the natural process.
Here's the Earth, sunlight's coming to it, heating the surface. The warm surface gives off radiation of another kind called infrared radiation. That gets trapped by the greenhouse gases, water vapor, carbon dioxide, and methane, and so forth. And that's re-radiated back to the surface, making the Earth the climate that we're accustomed to.
The climate as we're making it gets warmed by air conditioners, traffic, and leaking steam pipes. Concrete soaks up more heat than grass and trees. Buildings absorb heat on hot days and release it during cooler nights. Summer nights sizzle as many as 9 degrees hotter in New York City than in the surrounding suburbs. This so-called heat island effect creates wind as well. When the heat rises, air moves in from surrounding areas to fill the gap. If all of this seems harmless, it isn't. We are pouring carbon dioxide into the atmosphere at record rates. CO2 and other greenhouse gases from burning fossil fuels have raised temperatures around the globe. The 14 warmest years on record have all occurred since 1980. If warming trends continue, we'll see more destructive storms and flooding, melting ice caps, and rising sea levels. Some scientists think we can modify the climate on purpose and fix the changes we made by accident. These geoengineers suggest repairs on land and in the ocean. A few suggest planting more trees to take out the excess carbon dioxide. But it will take 16 acres of trees per person to take out the 5 tons of carbon in the atmosphere each of us statistically puts in. Others want to salt the seas with iron and produce more carbon-consuming plant life in the ocean.
In this experiment, we injected less than half a ton of iron, which promoted enough phytoplankton growth to draw down 2,500 tons of carbon as carbon dioxide.
But where will all that carbon go when the phytoplankton breaks down? The fact is, unless we can limit our dependence on fossil fuels, we will have to take drastic measures to avoid the fallout from man-made weather.